Hi. So on the last video, we were solving the example 2.10 from the topic 2.6.4, which is about transformations relative to a rotative reference system. So we saw that we can do transformations in relation to a fixed reference system and in relation to a rotative reference system. The fixed reference system is the fxyz ref system, and the rotative one is the fnoa. So now you know that is possible to do transformations in relation to these two reference systems. And also we can have other reference system uh, as we are dealing with problems with more complexity. And I said that on this video we will solve the example 2.11 and 2.12 if we have time. But before, we need to get back a little bit when we saw how to write a transformation in a equation form like you are seeing right here. So we can represent a transformation in the form of a equation. So this equation tells to us that we can find the final position of a point of and rigid body after the transformation with a initial position, initial coordinate of the rotative reference system, which is fixed on a fixed reference system. So this is what we have been done all this time, and that is the fixed reference system, and we fix this rotative reference system on the origin of this one and OA, and we need to get back to this because to solve the example 2.11 we need to know how to write this equation in a conventional form that make easy to follow the relation to different types of transformations. So we can write this equation in another form, and it's going to be the form that we are been using throughout this book, throughout this series of videos. So I have already right here how we can read these notations. Um, these notation, which mean the coordinates of the point on the reference system f x y z. We read as the point in relation to the referential u, and we write this notation on this form, and this notation, rotation above or around the axis x with some theta angle, we write with this notation transformation of the referential, or in relation to the referential u. So is the transformation of the referential with some respective universe. And I have already some example right here. So we have these notations. U for universal, we have R for robot, but this is all referentials. So the referential of the robot, a universe referential, the referential of some piece, the referential of the end effector, and the referential of the hand of the robot. These are referentials. And finally, we have the coordinates of the point of the fixed reference system, rotative reference system, sorry, which is P in relation to the referential or. So that's how we read this notation. P in relation to the referential or. So throughout this book, throughout this series, we will be using this formula, this notation, because it makes more easy to represent different referentials. And with that being said, let's get started and solve the example 2.11. So on the example 2.11, it says that a referential B it was rotated 90 degrees in relation to the axis x, and then it was translated in relation to the current axis A 3 inches. So notice that we are doing transformations in relation to the fixed referential and in relation to the rotative referential. And this before being rotated ninety degrees in relation to the axis Z. And finally, it was again translated 5 inches in relation to the current axis O. So we are doing transformations on the rotative reference system and on the fixed reference system. So he asked for us on the letter B to write an equation that describes the motions, the movements that are being done. So we need to identify each transformation. So we have a rotation of 90 degrees in relation to the axis X. So is a rotation around or above the axis X of 90 degrees. We have a translation in relation to the current axis A, 3 inches. So is a transformation of translation. Of 3 inches. And he says that is on the axis A. So it's NOA. We have a rotation of 90 degrees in relation to the axis Z. So we have another transformation of rotation, but now above or around the axis Z. And finally, we have another translation of 5 inches in relation to the current axis O. Okay? So he asked for us to write an equation that describes these movements. So we have to remember how to read this notation. Translation of the referential in relation to the referential U. And we are doing a transformation in relation to the referential B. So is a transformation in relation to the referential B with some respective universe. So is rot of Z of 90 degrees, rot of X of 90 degrees, followed by translations, transformations. And that's it, the letter B. And on the letter, sorry, the letter A, and on the letter B, he asked for us to find the final position of a point P with the following coordinates 1, 5, and 4. This T means transpose it, and if we transpose these coordinates, we got the matrix form, just this, um, which is fixed on a referential in relation to the reference system. Now we have to use this equation, and as I'm saying, is the equation that is the notation that we will be using throughout this book, throughout this series of videos. And that is the transformations that are being done, and we will find the final position of this point in relation to a universe after the transformations on the referential B with the respective universe, and multiplying this by the coordinates of the point in relation to the referential U, but now is in relation to the referential B, in relation to the referential B, not the universe, the is the referential that we are using, the referential B. If we change right here, it's B. Um, Again, we need to get back and use the characteristic matrices of periodization. We are not doing periodization. We are doing successive transformations of rotation and translation. But we need to know the characteristic matrix of a rotation above some axis. Let me paste right here. And the first transformation is above or around the axis x, and that is the characteristic matrix of a rotation above the axis x. and we just need to substitute uh, by cosine of 90 and sine of 90, and we also need to add the scale factor W to keep this matrix on the quadratic form. 0, 1, minus 1, and 0, minus 1 and 0, and adding the scale factor to keep this matrix on the quadratic form. So this is the scale factor. Now is um, a rotation above or around the axis Z. Zero, 1, minus 1 and 0. And adding the scale factor W to keep this matrix on the quadratic form. And for the transformation, uh, we have to remember that when we are doing a translation, we do not have any transformations around the any transformation of rotation around the axis. So we got a identity matrix. So you can identify a transformation of translation uh, every time you see this identity matrix. So that is the characteristic of a identity matrix. And is being translated of 3 inches is NAO, NOA, sorry, NOA, and we have another transformation of translation but right now is 5 inches on the axis O. Okay, and we have to multiply this by the initial position of the point, the coordinates of the initial position of the point. So the coordinates of the initial position of the point, and doing the transposed form and adding the scale factor 1 to keep this matrix on the quadratic form, and doing this multiplication, we are left with the final position of the point. And that's it. So on this video, we saw uh, the other way to write this equation, which is the way that we are been using throughout this series of videos, throughout the book, because this way it makes easy to follow the relation uh, between different transformations. And we also saw how to read these notations, which is very important. This formality is essential. And that's all for now. And on the next video, we will solve the example 2.12, which is the same as this one, transformations in relation to a referential. And that's it. Thank you. See you in the next video. Bye bye.